Alright guys, we're moving on to section 6.1. The title of this section is Discrete and Continuous Random Variables. And for whatever reason, students usually have a hard time with this section, so you might have to go back and watch certain parts of this video multiple times until it sinks in for you. So, a couple of vocabulary terms. It says a random variable takes numerical values that describe the outcomes of some chance process. And the probability distribution of a random variable gives its possible values and their probabilities. So I'm kind of skipping forward a little bit, but this is a probability distribution because here's the values the variable can take, and there's the probabilities of each variable. Okay. So there are two main types of random variables. There's discrete random variables, and there are continuous random variables. So here it says a discrete random variable takes a fixed set of possible values with gaps between. Alright, the probability distribution of a discrete random variable gives its possible values and their probabilities. The probability of any event is the sum of the probabilities for the values of the variable that make up the event. So there are several steps for discrete random variables. Step 1, give your variable a name, i.e. x equals the number of children you plan to have. You set up a table listing all possible values of x, and sometimes this is done for you. Write in the associated probabilities that are given in the problem. Again, sometimes that's done for you. And the conditions are that the probability of all the x values must be individually between 0 and 1, and the sum of all probabilities must add to 1. So I'm going to skip forward real quick to this question again. So here's all the values that the variable can take, 0 to 10. Each probability, each one of these individually has to be a number between 0 and 1. And if I add up all of these probabilities, they have to equal 1. Okay. Now, all right. Now what makes this a discrete distribution or a discrete random variable? Well, notice I start values at 0 and I end at 10, but I don't have any number between 0 and 1. I don't have any decimal. These are discrete numbers. There's not numbers in between. Okay, so it's not continuous. It's discrete. So the example we did up here about the number of children, that would be a discrete distribution because you can only have whole numbers of children. It is not possible to have 1.5 children, nor is it possible to have any decimal number of children. So the number of children, you could have 0, you could have 1, you could have 2. They just take on whole number values. Okay, they just take on whole number values. So there's nothing in between. That's what makes it discrete. So let's look at this first example. It says, in the year 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth, which were skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0, 1, 2 scale to rate a newborn on each of the 5 criteria. So if the baby, for instance, had really good skin color, that baby would get a 2 on that factor. If the baby had really good heart rate, then they would get a 2 there. So when you take these 5 things, if the child measures high on all of them, they would get 2s on all of them, and when you add them up, 2 times 5 is 10. So they can get a max score of 10. Or if they got 0s on all 5 criteria, 5 times 0 is 0. Or they could get any integer in between. Okay? It says a baby's Apgar score is a sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. Apgar scores are still used today to evaluate the health of newborns. The table below gives the probability distribution for x equals Apgar score. Okay, so x can take on the values from 0 to 10, all whole numbers in between. All right. All right, y'all, sorry about that. Okay. So part A, it says show that the probability distribution for X is legitimate, for APGAR score is legitimate. So the way I would do that, the only way it's a legitimate probability distribution is if all of these numbers add up to 1 and their individual probabilities are between 0 and 1. Well, that's definitely true. But is this true? What is the sum of the probabilities of each APGAR score? All right, so I would have to take 0.001 plus 0.006 plus 0.007 plus 0.008 plus 0.012 plus 0.020 plus 0.038 plus 0.099 plus 0.319 plus 0.437 plus 0.053. So go ahead and put those numbers into your calculator and see if they add up to 1. So 0.001, I'm just doing it. Hopefully you're doing the same thing in your calculator. I think I missed one here. Okay, so when I did that, I got 1. So there we go. The sum equals 1. The sum of all of these probabilities equals 1. So it is a legitimate probability distribution. Okay, it's discrete because these can only be whole numbers. We can't have all the numbers in between 0 and 1, all the decimals. All right, so part B. It says, using your calculator, make a histogram of the probability distribution and describe what you see. So the way I'm going to do this, okay, is if I go under my lists, in list 1, I'm going to type in all the APGAR scores between 0 and 10. So I've already done that. And in list 2, I'm going to type in their associated relative, these are, the probabilities are actually the relative frequencies. And these are the relative frequencies. So when you have that data entered, go ahead and quit out of that. All right, then go into your y equals, get rid of any graphs you might have, but let's make a statistics plot. So turn plot 1 on, and let's choose the option that's a histogram. It's the third option. Your X list, that is APGAR score, that should go, that was in list 1. But we're going to treat the probabilities as relative frequencies. So probabilities as decimals, this is like relative frequency. Okay. So we're going to put that into list 2. All right. And then once you do that, you can do it any color you want. I'm just going to choose to do it in red. All right, and let's do a zoom 9. Okay, it gives me that, which doesn't look great. So I might have to go in here and change my window. Let's go from -1 to 11. Let's go 1 less than this to 1 more than this. Okay. All right. Let's scale it by ones, by one tick mark. All right. And for the y scale, what's the biggest probability relative frequency that you see is 0.319. So we know we're never going to get less than 0, but we know we're never going to get more than 0.319. So maybe I can go up to 0.35. Maybe I want to scale these by 0.05. Okay, now hit graph. Oh, I'm sorry, the biggest was 0.437. So that's why I don't see one of those. So maybe go up to 0.45 and hit graph. There we go. So this actually made the histogram for me. If I hit trace now, let me zoom in so you can see it. All right. So here, there's nobody between -1 and 0. All right. Because if you see here, it says n equals 0. All right. Now this says how many people, or what's the relative frequency for 0 to less than 1? That would only include 0 here. Okay. Well, the probability there is 0.001. Then we get 0.006. So our calculator will do a relative frequency histogram for us as well. Okay, so it looks like that. So there's definitely a left skew here. Hopefully you can see that this distribution has some sort of left skew. All right. So, when we put the APGAR scores on the x-axis, and we put the probabilities of the APGAR score, so xi, those are the actual APGAR scores, and then you can just kind of copy it over. Okay, you can copy it over. So it's really, really small at the beginning. Then it gets a little bit bigger. So it kind of looked like that. That's what our relative frequency histogram. So let's read part C. It says, doctors decided that APGAR scores of 7 or higher indicate a healthy baby. What's the probability that a randomly selected baby is healthy? So what they're saying, the probability of healthy baby means that the probability needs to be 7 or bigger. That means x has to be greater than or equal to 7. All right, so we're going to focus in on APGARs that are 7 or higher. But if I want to find the probabilities, then I need to add these parts together. Okay, so what I need to do is I need to add the probability that x equals 7 plus the probability that x equals 8 plus the probability that x equals 9 plus the probability that x equals 10. Okay. So that would be 0.099 plus 0.319 plus 0.437 plus 0.053. So let's do that on a calculator. So when I do that, I get 0.908. So what does that mean? There's a 90.8% chance that the baby would be called healthy. Now, there's two ways to do the second part of the question. The next part of the question says, what's the probability that it's not healthy? So one way to do that, not healthy, would mean less than 7. Okay, so what that would mean is, what are the numbers that are less than 7? Well, they're all of these numbers. Okay, they're all of these numbers that are less than 7. So the probabilities would be, I would have to add these numbers here. But we also know that this green part of the probabilities plus this blue part of the probabilities, altogether they equal 1. So an easier way to do this would just to be 1 minus the probability that x is greater than or equal to 7. because we already know that part. That's 0.908. All right. So if I just do 1 minus 0.908, I would get 0.092. That's a much easier way. Okay. That would be exactly the same thing as if you added this, plus this, plus this, plus this, plus this, plus this, plus this. Okay. Because all together, these things add up to 1. We already know that that makes up 90.8%. So how much does this have to make up? 9.2%, which is this number right here. All right. So when we have a discrete random variable, such as the APGAR score example we just did, there's certain ways there's different ways to find the average for a random variable, okay? So to find the mean, okay, what it tells you on your formula sheet, it gives you this formula. It says mu of x equals the sum of xi times p of xi. So what that formula does, it says take each value of the random variable and multiply that by its associated probability, then sum them to find the mean. All right, and we're going to get into this formula. How do you find the variance of a discrete random variable? Well, okay, on your formula sheet, it gives you this formula. Okay. And we'll do an example of that. And after you find the variance, you can find the standard deviation. And just make a note here on your note card. That's a square root. So to find the standard deviation, take the square root of the variance. So, using the APGAR example, okay, calculate and interpret in context the mean, which means the expected value. So these words are synonymous. I'll do the same color. Mean, expected value. They can use either one of APGAR scores by hand. So to find remember, we're letting x equal the APGAR score. Okay, so to do part A, to find the mean APGAR score, we would call that mu of x, the mean APGAR score. Okay. Well, what does the formula tell us? That means we take the sum of the actual APGAR scores times the probability of that APGAR score. Okay. So going back to the previous page, the first APGAR score we have is 0. And the probability of getting an APGAR score of 0 is 0.001. Okay. So we would do 0 times 0.001. But we have to do that for all the APGAR scores. The next APGAR score is 1. And what's the probability of getting a 1? It's 0.006. Okay. The next APGAR score is 2. So we do 2, and the probability of that is 0.007, plus 3 times 0.008, plus 4 times 0.012, plus 5 times 0.020, plus 6 times 0.038, plus 7 times 0.099, plus 8 times 0.319, plus 9 times 0.437, plus 10 times 0.053. So go ahead and do that on your calculator. And I'm going to do it too. Make sure we get the same answer. Just be careful when you're entering it. And you can do this all at once. hopefully I didn't make any mistakes, but when I did all that, I got a value of 8.128. So that can be called the mean APGAR score, or we can say that's the expected value. So we can also call it capital E sub x, or E of x. All right. So here, babies, newborn babies have an expected, or mean APGAR score of 8.128. Okay. And this is okay that this is a decimal, okay, because averages can be decimal. So for example, on one test, if you make a 74, and on the next test you make a 75, your average is 74.5. Even though you can't make 74.5 on a test, you can get an average of 74.5. Right. So that's how we do that by hand. That's how we do that by hand. All right. Now part B. Part B asks me to calculate the variance. Variance means spread. Okay, so I'm trying to find the spread of this. So it says calculate the variance of APGAR scores by hand. So the symbol for variance is sigma squared. So I'm finding the variance of x. And sometimes it can be written like this. They might say var of x. Okay. Variance of the variable x. All right. So this formula is a little harder. So here's how we do this. Okay. We need to take the sum of the individual APGAR scores minus the mean APGAR score squared times the probability of the individual APGAR scores. All right, so the first APGAR score we had was 0. So the first xi we get is 0. Minus, well, what is, hold on just a second here, guys. Minus, what's mu of x? Well, we found mu of x to be 8.128. Okay, so that was the mean. All right, so this APGAR score is 8.128, less than the mean. But with variance, remember we have to square variance. But now I need to multiply that times the probability of getting a 0. And the probability of getting a 0 is 0.001. And you got to do that for all the APGAR scores. So that's the first one. Okay. Now the next term, so this is just the first term. All right, and then the next one, we have to do the individual value, APGAR score of 1, minus the mean, squared, times the probability of getting a 1. Okay. So that's the second term. We're going to keep going. All right, then we have 2 minus 8.128 squared times the probability of getting a 2 was 0.007. So that's that term. All right, plus, we have 3 minus 8.128 squared times 0.008. Plus 4 minus 8.128 squared. And don't worry, I'm gonna tell you how to do this on the calculator real easily. 0.012 plus 5 minus 8.128 squared times 0.020 plus 6 minus 8.128 squared times 0.038 plus 7 minus 8.128 squared times 0.099 plus 8 minus 8.128 squared times 0.319 plus 9 minus 8.128 squared times 0.437 plus 10 minus 8.128 squared times 0.053. All right, so it's a long string. So take a few minutes and let's go ahead and do that in our calculators. I'm just going to do one shortcut real quick. I'm going to put 8.128 there, and I'm just going to store it as A. That'll kind of reduce some of the work I have to do. So like on the first one, I can do 0 minus, but instead of typing in 8.128, I can just go 0 minus A squared, okay, times 0.001. So it's going to save me a couple things, then plus, and I'm just going to keep going. I'll go 1 minus that squared times 0.006 plus 2 minus that squared times 0.007 plus 3 minus that value squared. Remember to put parentheses. Okay. 0.008 plus 4 minus that squared 0.012 plus 5 minus that squared times 0.020 plus 6 minus that value squared times 0.038 plus 7 minus that value squared times 0.099 plus 8 minus that value squared 0.319 plus 9 minus that value squared times 0.437 plus 10 minus that value squared times 0.053. Okay, so it's a really, really long string. Okay. Hopefully you have something similar like that. I did save myself a few keystrokes by just putting the A in there, by storing that to mean as A. You can store it whatever letter you want. Just makes it a little bit quicker. And I'm going to show you how to do this on the calculator a lot easier in just a second. So I do that, I hit enter, and there's my variance, 2.065616. Okay, so the variance that we get here is 2.065616. All right. So once you do that, once you know the variance, you can find standard deviation a lot easier. So to find standard deviation just has the symbol sigma. So we're finding the standard deviation of APGAR scores. All we have to do is take the square root of the variance we just found. So the square root of 2.065616. So I take the square root of that, and I get 1.4372. Okay. So here's my standard deviation. Now, what's the interpretation of the standard deviation? On average, a baby's APGAR score deviates 1.43 APGAR units away from the mean. So this is the average amount of spread, the average amount that a baby's score deviates from the mean. All right. Now, we can do all of this in one much easier step. So, remember we put the data into list 1 and list 2. List 1 was the APGAR scores, list 2 were the probabilities or the relative frequencies. no matter how you want to say it. Okay. Here's how you can do it very, very simply in the calculator. All you have to do is you have to go stat, go over to calculate, and this is still one variable stats. Now your APGAR scores are your list, but you do have relative frequencies. Those are the same things as probabilities, so you put list 2 there. Okay, and then just go calculate. And when you do that, notice here, it gives you X bar, it gives you the mean, 8.128. That's the exact same number we get there. Notice, it will not give you the variance though, but it does tell you the standard deviation right here, 1.4372. 1.4372. Now, if we wanted variance, all we would have to do is go 1.4372, I think there was another 2 after that, and square it. So if you square standard deviation, I'm back to 2.0656. What do you notice here? 2.0656. Now it's a little bit off after that because I rounded, okay? Because I took this rounded number and squared it, all right? But if you want to get variance, just take standard deviation and square it, all right? But you can do that in one step in the calculator. So again, your data is in list 1 and your probabilities are in list 2, and we go stat, calculate one variable stats. Our list is in L1 and our probabilities are in list 2. Calculate the 2 numbers we care about. Is this number the mean or the expected value? And this number is the standard deviation. All right, so that's discrete random variables. Variables that take on fixed values. And the values, there's no values in between. All right, now, this is a little different than a continuous random variable. A continuous random variable is a variable that takes all values within an interval of numbers. The probability distribution of a continuous random variable is described by a density curve. The probability of any event is the area under the density curve and above the values of the variable that make up the event, just like the area of a normal curve between 2 values of the variable. The area under any density curve is exactly 1. It has to be, otherwise it's not a density curve. Okay, so exactly 1 corresponding to a total probability equal to 1 or 1.0 or 100%. If the density curve is not a normal distribution, we can use geometry to determine probabilities. So let's think about a variable that's continuous. Height, for example. Okay. Height would be a continuous random variable. So ask yourself, why is this a continuous random variable? Can someone be 70 inches tall? Yes. Can someone be 71 inches tall? Yes. Can someone be anywhere in between 70 and 71? Yes. Okay, and then they can be anywhere between 71 and 72. And it goes on forever, okay? Right, it starts at 0, but it can really go on forever this way. That's why it's a continuous random variable. So if I wanted to make a graph, a density curve for heights, okay, these are the heights. The heights would go on this axis, and it's continuous. So we're going to describe it by some sort of curve pattern. This one happens to be normal. Heights are normally distributed. Okay. So going on to the next page. So let's just kind of review normal distributions. All right. It says the heights of young women closely follow the normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. All right. So if I start to draw this curve, it says it closely follows the normal distribution, so I'm going to draw my bell curve. All right, and right down the center, I'm going to put 64, because that's the mean. All right, and it says standard deviation of 2.7. All right, so I'm going to say this is a normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. So I'm going to tell the reader that when I make my normal curve. Now choose one young woman at random. Call her height y. So y equals height of woman, of a single woman. Okay, single being just only one, not single referring to being with someone or not. Okay, so therefore y is part of a normal distribution. So I'm going to tell the reader y is a random variable that's normally distributed with that mean and that standard deviation. So that means if I go over one space this way, okay, that distance would be 2.7. Okay. Now, let's answer what the question is. It says, find the probability. So let's write it in probability notation, that the chosen woman is between 68 and 70 inches tall. So what does that mean? That means y has to be between 68 and 70, because y is our variable, so this is y. Okay, now where is 68? Well, this is only 2.7, so that would get me up to 66.7. So 68 is somewhere over here. Okay. 68 is somewhere over there. 70 is over here as well. So there's where 68 and 70 are on my graph. I'm trying to find this area. Okay. Now, we can do one of two things. We can convert these to z-scores, and then we can use our tables to find the area to the left of that. But an easier method is just to use the calculator. Okay? Just use your calculator. Now, how do we do that with the normal curve? We go under our distributions menu, so second, vars, go to normal CDF. Okay? What's the lower bound of the area? 68. What's the upper bound? 70. Okay, so I'm going to put that in for lower and upper. What's the mean of this distribution? Well, it's 64. What's the standard deviation? It's 2.7. And I hit paste, and there we go. It gives me the probability right away. 0.0561. Okay, there's the probability. There is a, let's change this into percent, there is a 5.61% chance that a woman selected is between 68 and 70 inches tall. So that's a normal distribution. Remember, this is continuous. It takes every number into account between 68 and 70. So it takes 69, it takes 68 and a half, it takes 68 and a quarter, it takes 69.99, it takes all of these numbers. That's why it's continuous. All right, now what about if you have a continuous distribution, but it's not normal, it's not a bell curve? Well, before we do anything, let's make sure this is a valid density curve. So if you look at it, it's a triangle. It is a triangle. And the values that the variable can take are between 0 and 2. So if you remember how to find the area of a triangle, we say 1/2 base times height. All right. So the area here is 1/2. What's the base? How long is the base? Well, it starts at 0 and it ends at 2, so it's 2 units long. Okay, how tall is it? All right, I'm assuming that's a right angle, so it's 1 unit tall, so its height is 1. Well, 2 times 1 is 2, and half of 2 is 1. So does the area equal 1? Yes. This is a valid density curve. Okay, because the area equals 1. Okay. So let's answer the questions. All right, part A, what's the probability that x equals exactly 1? Well, where is 1 here? 1 would be halfway between 0 and 2. So if I draw a line up to where it meets the triangle, this right here has no area. It's only one-dimensional. Okay, so a line does not have any area. So the probability that x equals 1 is 0. There's no area for a line. Okay, there's no area for a line. Now, let's try the second part. Okay, let me redraw this. Here it's asking, what's the probability that x is greater than 1? Okay, so here's the x values. So what we're going to do is we're going to draw a line up at 1, but we want x to be bigger than that. So what I'm trying to find here is I'm trying to find that area, that shaded area. Well, if you notice, that shaded area is another triangle. All right. So if you think about this, when I go from 0 to 2, I start at a height of 1 and I end at a height of 0. Okay, it's going from a height of 1 down to a height of nothing. Well, if I go halfway between 0 and 2, then this is going to hit on the y-axis halfway between 0 and 1, which would be a half. So when I think about this little red triangle here, this has a base of 1 because 2 minus 1 is 1. And what's its height? This height right here is only a half. So I'm going to use geometry here. Area equals 1/2 times base times height. So the area would equal 1/2. The base is 1 unit long, and the height is 1/2. Okay, so 1/2 times 1 is a half, times another half is a fourth. Therefore, the probability that x is greater than 1 equals 1/4, or as a decimal, 0.25. Okay, so let's try the last one. The last one is kind of difficult. So here's where 0 was. Here's 2. All right. Here's where 1 was. And we already took that over. We said that that happened at a half. But here I want to know what's the probability that x is between 0.5 and 1.5. Well, where's 0.5? 0.5 is halfway between 0 and 1. So where's it going to hit here? Well, it's going to hit halfway between a half and 1. So halfway between a half and 1 would be 3/4. And if I think about this, where's 1.5? There's 1.5. Take it up. So it's 1.5 is halfway between 1 and 2. So on the y-axis, it's going to hit halfway between 0 and a half. So halfway in between that would be a fourth. Okay? So when I do my shading, what I'm really interested in is I want this area. I want the area of that trapezoid. I want the area of that trapezoid. So the picture that I get here for the trapezoid looks like this, if I draw it accurately. There's the trapezoid. So this is base 1 of the trapezoid. This is base 2. And this is the height. All right. So how do you find the area of a trapezoid? Okay. You take the height over 2 times the sum of the bases. Okay, so what is this height right here? Well, I started at 0.5, I ended at 1.5. Okay, so the height is simply 1. So I do 1 over 2 Now base 1, this is base 1. All right, that's base 1. How high does it go? It goes 3/4. What about base 2? That's base 2. That only goes up 1/4. All right, so that's 1/4. So if I simplify this a little bit, I get a half. 3/4 plus 1/4 is simply 1, and a half times 1 is a half. So the probability that the x value falls between these two is simply a half, or 0.5. So in here, this is half of the area of the triangle, of that big triangle. So that's how you do continuous distributions that are not normal. You got to use your geometry knowledge. And that's where we're going to cut it off for today. So we talked about discrete random variables, and we talked about how to find the mean and how to find the mean and how to find the standard deviation of discrete random variables, and we talked about continuous random variables. Now, I don't think they're going to do this on the test, but what about if you were asked to find the mean here? Okay, or more likely, how would you find the median? Okay, if you think about the median, all right, the median is the 50th percentile. All right. So what you would be looking for an x value that would separate this graph to where the area on the left would be 0.5 and the area to the right would be 0.5. So you could use a little bit more complicated algebra to figure out where that is. Okay. All right. It's more of an optimization problem. I don't think they'll give you any problems like that, but you might be able to logic your way through where that would have to be. Okay. Same thing if they asked you for Q1. Q1 is the 25th percentile. All right, so what x could you take up that would be 25% to the left? Or they might ask you Q3, or they might ask you IQR. I do not think they're going to do that. That takes way too long. Okay, I don't think they're going to give you that. Okay, or if they do, it's going to be a multiple choice, and you could plug it in and see if it works. So we'll stop it there for today. Thank you for watching.